All right, in this lesson, we're going to again be looking at explosions, but we're going to be looking at a situation that has a little more complexity to it in that we're going to be giving the initial momentum of the system a value other than zero. So we're going to be giving the objects that are going to be exploding apart an initial speed of 1 meter per second, and then we have the explosion, and then we're eventually going to have our 2 kilogram particle slam into a brick wall and come to a stop and analyze what is going on during this entire event. So there's a lot going on in this problem, and hopefully we have all the tools we need to understand everything that is going on. So let me erase my markers here, and let's see what we have. Well, the first thing that we're calculating is the velocity of the center of mass of the two particles prior to the explosion. Well, the center of mass position itself certainly would be closer to the 2 kilogram mass than the 1 kilogram mass, but since they're both moving at 1 meter per second, there's no calculation to make. The velocity of the individual particles is 1 meter per second, and the velocity of the center of mass is positive 1 meters per second. So at some later point in time, we have the explosion. Boom. So the explosion occurs for all explosions. P initial equals P final, because during the explosion, we are assuming that any external forces are negligible by comparison to the force of particle 1 on particle 2 and particle 2 on particle 1, because the explosion happens so quickly over such a short period of time. Well, we know the initial momentum of the system was 3 kilograms meters per second, based on the fact that we had the entire system rolling along together at positive 1. Now, after the explosion, we are told that the 1 kilogram particle is actually moving backwards at negative 3. So we have the 1 kilogram particle moving backwards at negative 3, and we're asked to solve for the velocity of the second particle, the 2 kilogram particle, going forward. And we're going to use P initial equals P final. So P initial was the plus 3. P final is here. And we can calculate the velocity of the 2 kilogram particle has now increased from the 1 meter per second it was moving prior to the explosion to now it's moving at 3, not kilograms, just 3 meters per second in the x direction. All right. Now, the final velocity of the center of mass remains unchanged because there are no external forces. So if there are no external forces, the acceleration of the center of mass is 0, which means the only way the acceleration can be 0 is if delta v, right? Acceleration is delta v over delta t. If that is 0, so the acceleration of the center of mass being 0 dictates that the velocity of the center of mass remains unchanged. And again, there's no calculation to make. We just have the velocity final at plus 1 meters per second. Okay, well, how much kinetic energy was released during the explosion? The energy released during an explosion is always the change in the kinetic energy of the bomb and the pieces. So initially, we have the kinetic energy of the system being the 3 kilogram system moving at 1 meters per second. So it's final minus initial. So the initial is both together, 3 moving at 1. Now, after the collision, we calculated that the second particle, the 2 kilogram particle, is moving with a speed of 3 forward. We were told that the 1 kilogram particle was observed to be moving backwards at 3. So we get 13.5 joules after the explosion. We had 1.5 joules prior to the explosion. So we have 12 joules total that was released during the explosion. So that is the energy of the explosion. And the final part of this problem is actually an interesting twist to the problem. How will the velocity of the center of mass change if now an external force is going to bring velocity 2, mass 2, to a stop? So we had the 2 kilogram mass going forward at 3 meters per second until it hits the wall. When it hits the wall is going to exert a force to the left. So there's going to be a wall force to the left on the 2 kilogram object, which is part of the system. So that wall force to the left brings the 2 kilogram mass to a stop. So now when I calculate the velocity of the center of mass of the system, I actually get that it's moving backwards at 1 meter per second. And hopefully that makes sense based on the fact that the external force that was exerted on the system by exerting itself on the 2 kilogram mass was to the left, and now, based on our calculation, is going to drive the center of mass actually back to the left along with particle 1, which is the only particle moving, and it's moving to the left. So, again, I know this was a problem that had a lot going on in it, and I'm going to erase my additional annotations other than to go back and scribble out the kilograms here because the velocity is just meters per second. And hopefully, again, based on what we're learning and understanding, that this is all beginning to fall into place, and we will be moving on with more examples.